By Luca Iliesiu, who will be telling us about the volume of the black hole interior at late times.
Thank you very much for the invitation, and it's great to be back in person. So today I'll be describing how the volume of a black hole interior behaves at very late times, and this is work in collaboration with Mark Mitzi and Gabor Sarasi. But as Jurek mentioned, I'll also comment on the relation between this volume observable that I'll first discuss in GT gravity and the volume observable in the factorizing theory that Jurek just told you about. To start, I want to remind you of a puzzle that was brought up several times yesterday. And it's a puzzle in ADS-CFT about the growth of the volume of the black hole interior. So on the left side, I have the Penrose diagram for an eternal black hole in ADS. What I say is more general than for eternal black holes in two-sided eternal black holes in ADS. It's more general, it applies in various settings, but for now we'll focus on that setting. And on the right-hand side, I'll show you what the classical computation in general relativity tells you that volume behaves like as a function of time. I'll normalize, I'll subtract here when I plot the volume, I'll subtract the volume at time t left equal t right equal to 0. So at t left equal t right equal 0, I'm actually preparing on the boundary side the thermal field double state. And I'll evolve the thermal field double state with a combination between the left and right Hamiltonians. Up to time t equal b, there's some transient behavior. The volume grows, but the growth slightly depends on the exact nature of the black hole. Maybe it depends on its charge. Maybe it depends whether it's a Schwarzschild black hole. But after this thermalization time, the growth is linear, and beyond that, classically, there's no reason for this growth to stop. In fact, if I take time going to infinity, I can easily compute what the volume of this maximal slice is, and I can see that as t goes to infinity, the volume of the black hole interior also goes to infinity. So that's a slight puzzle on the boundary side, because we're used to see on the boundary side that Euclidean correlators at least thermalize, and they thermalize in the time proportional to beta, so local operators don't tend to grow for such long times. So the concrete question is, in the boundary dual of such a state, the thermal field double state, what grows long after the thermal equilibrium is attained? And there has been a proposal that was brought up yesterday for what such a quantity is. And the proposal is that this quantity is the circuit complexity for the thermal field double state as it evolves in time. So what I mean by the circuit complexity is the minimum number. If I imagine some discretized version of my boundary theory, maybe some lattice regularization, then one could compute the minimum number of gates, C of t, required in a circuit given a universal set of gates. I can compute the minimum number of gates C of t that are required in order to construct a circuit going from the thermal field double at state 0 to the thermal field double at time t. So let's see how this circuit complexity behaves in time. And yesterday we heard several talks about that as well. Beautifully, people have shown that the complexity grows linearly in time for a long time, after which at the time proportional to the number of degrees of freedom of the system, in this case, since we're studying black holes, the number of states is roughly proportional to e to the black hole entropy. The complexity is expected to plateau since I can always construct an appropriate circuit with this number of gates. And it's expected to plateau also at a value that's proportional to the number of degrees of freedom in the system, or the effective size of the Hilbert space. Now, this brings a slight problem with the slide that I showed you earlier. The small problem is that, at least from a classical point of view, I saw that there's no reason, at least naively, to expect that the volume of the black hole interior wouldn't grow forever. So while indeed this linear behavior is smashed at small times, There was a question about what happens at very late times, namely at times proportional to e to the s black hole. This is usually, the question that we'll answer today is why would the volume of the black hole interior plateau? And usually the reason why people claim it plateaus is that at late times there is a breakdown of general relativity, but to me that's a little bit vague. So what I want to do is concretely explain how the breakdown of general relativity occurs at late time and precisely reproduce a plateau for the volume. So since it's late, I'll first review my main results so you guys can relax. We will show that including a sum over geometries with different topologies, so geometries that include wormholes, and the gravitational path integral will lead to the desired plateau for the volume. On the other hand, given that you just heard Jorrit's talk and in a UV complete theory, we expect the factorization to occur and maybe wormholes are not present at all, why should I even care about a computation that involves wormholes? This brings me to my second point, which is that the volume of interior will be shown to be a self-averaging quantity up to very long times, including times that are much larger than e to the s black hole. And I'll tell you exactly what that means in a few slides. And we will use this to show that the volume of the black hole interior also plateaus even in the gravitational theory where a factorization is achieved, namely in the theory that Jorrit just described. The third point is that the exact computation of the volume in the bulk points to a dual boundary quantity that is much simpler to compute than the circuit complexity, but has similar time dependence. So as most of you know, and if you've been here yesterday, the circuit complexity is an incredibly difficult quantity to compute, especially for a time-independent Hamiltonian. It's desirable to have a quantity that doesn't have the same ambiguities as complexity, and we'll find such a quantity. And we'll call this quantity spectral complexity. And we will show that it also has a straightforward information theoretic meaning, although we won't be able to directly connect it to circuit complexity. Okay, so with these results in mind, let me tell you what the model that we study everything is in. So in this particular talk, I'll be talking about JT gravity, even though the results that I talk about are applicable beyond JT gravity to a much vaster class of chaotic systems. Yes?
So you have some specific definition of black hole interior as a function of time, but you can definitely define it differently.
Okay.
For example, you can go back to the scrambling, surface. The straight horizon, and then from that define for example, the horizon interior.
Yes.
Then is it not growing linearly, for example, as a function of time, or it may grow?
I think even if you define it from the horizon, even if I don't know whether what you said is a diff invariant quantity, I have to think about it. But even if usually we have to define diff invariant quantities in order to compare it to boundary observables. So I'm not sure whether what you said is diff invariant, but I think the initial paper of Stanford and Susskind, they actually computed the length of the between the horizons themselves. And I think they also found a linearly growing function of time. I have to look back at it. But yeah. An important, and we'll study the gravitational path integral of the theory, and an important role in our definition for the volume of the black holes will actually be played by the group of large diffeomorphisms. So large diffeomorphisms are also referred to as the mapping class group, and these are the set of transformations and the set of diffeomorphisms that are disconnected from the identity. A second important ingredient that we'll be using in today's talk is we'll be using Schatz, Schenker's Stanford finding that this model of JT gravity, or even more general models of dilaton gravity, are all equivalent to matrix integrals. where if I want to compute the partition, multi-boundary partition function, such as the one portrayed here, so I'll portray asymptotic boundaries between lines, one simply has to insert in the matrix integral a series of thermal partition functions of the matrix H. So let me tell you how concretely in this model, what's the tool through which we can compute the volume given this path integral. So we'll want to compute the volume in the thermal field double state. So the thermal field double states could be prepared by some Euclidean preparation. And I'll also evaluate it in the thermal field double state at a later time, which can also be prepared for Euclidean preparation. And in between these Bra and Ket states that are prepared in Euclidean signature, I have some region of Lorentzian evolution, where I specify the boundary time of a left point and a right point. My goal, since I'm in 2-dimension and the volume there is simply measured by a geodesic length, will be to measure the geodesic length between the point on the left and the point on the right. Now, importantly, in this prescription, I have to see what happens once I account for all configurations that could, for instance, connect the Bra and the Ket. So this will force me to consider what happens to this volume or this geodesic length once I go on higher topologies. So an equivalent question is, in the matrix integral, what is this definition of this length operator, the operator that measures the length of this red line in JP gravity? So on the disk, everything is simple. I'll evaluate things in Euclidean signature, and given my construction with the Bra and the Ket to be Euclidean prepared, I could just analytically continue my results to Lorentzian signature through the choice of T1 and T2 that I mentioned on the slide. On the disk, everything is simple because there's a unique geodesic connecting any two boundary points of the Euclidean disk. And in fact, that computation for the length of the geodesic on the disk was done in the paper by Yang. And I'll describe the results in a few slides. Where things get complicated is if I go to higher genus. So at higher genus, surfaces bring more ambiguities. And the reason why there are more ambiguities is because on any higher genus surface, starting with genus 1, there's actually an infinite number of geodesics connecting any 2 points on the boundary. So there's an infinite number of geodesics connecting the left observer to the right observer, let's say. So here I showed one of them, and I'll focus just for concreteness on genus 2. But this is another geodesic that also connects the same two boundary points. The question is, when I assert the length operator, when I want to measure this operator geometrically, with respect to which curve do I measure it? And you see, previously, a couple of slides back, I told you that the mapping class group or large diffeomorphisms are important, and you should know that this is a trick question. And the trick is that the two geodesics that I showed you on these slides are actually related through a large diffeomorphism. Namely, if I do a twist of 360 degrees, which leaves the boundary completely invariant, I go from this geodesic to this geodesic. But I also change the which moduli I measure on this surface, on this 2D surface. So what this essentially tells you is that if in the gravitational path integral, I quotient out this group of large diffeomorphisms, I should be careful not to overcount these geodesics. So essentially, I should count these geodesics only once. So in order to better explain this and better explain how to compute the length of these observables, it will be useful to cut the surface. So cutting the surface separates the boundary into two distinct components and opens up the surface like this, a bit more. And eventually you end up with this cylindrical shape, which has two geodesic cuts one starting from each asymptotic boundary. And while it's easy to see that by cutting this surface, or maybe it's easy to see that by cutting this surface, I eventually can deform it into this surface, it might not be that easy to see that if I start cutting this figure along the red curve, I obtain precisely the same contribution, but this is a simple consequence of the fact that these two curves are related by a large diffeomorphism. So in order to compute the length operator on an arbitrary genus surface, I have to take into account sums over surfaces that look like this, and I only count them once, even though there's an infinite number of geodesics that seem to contribute to the observable, but the quotient reduces it to 1. But this is not the only surface that I obtain for the only type of surface that I obtain by cutting. Namely, there are other geodesics on a genus 2 surface that, for instance, separate the surface, as I've shown here, into two disconnected surfaces, each of genus 1. And there's another one which separates the surface into a piece that has genus 0, it's just a section of the disk, and a piece that has genus 2. And the point is that whatever surface I draw and whatever geodesic I draw on the surface, as long as it doesn't self-intersect, and I'm going to assume that the volume of the black hole interior doesn't self-intersect, they can all be classified into these free categories when the overall genus is 2. So essentially what I have to do to compute the expectation value of the volume of the interior is I have to sum over these free contributions. And while it might seem daunting to try to do this computation at first sight, I can make the following remark for any order in the genus expansion. The same type of geometries contribute to all orders in e to the minus s naught as in the spectral form factor. And so the same ingredients are needed to compute the length of the Einstein-Rosen bridge, in this case, as the ingredients that were used to compute the spectral form factor by Schad, Senker, and Stanford. Yes?
Are we interested in the red geodesic being minimal length in its surface? Or are you planning to sum over all the possibilities?
I'm planning to sum over all the possibilities. Well, first, there's the question of even though maybe I could compare these free contributions, but I will sum over all possibilities.
It's not 3 because each of them represents infinitely many, as you said before.
Yes, each of them represents infinitely many, but each of them give you a finite result. I could in fact keep track of the individual contributions from these surfaces if I wanted to, but the most convenient result is to sum over them. And yes.
And we're only including connected geodesics?
Connected. What do you mean by connected?
I mean, there are also disconnected geodesics.
You mean closed geodesics on this surface?
Yeah, we're not including.
Well, I think I would like the observable that I defined to only take into account the volume of the black hole interior. And if that's the case in Lorentzian signature, I think I only need to account for this open geodesics that go boundary to boundary.
But there are also ones which are the union of such an open geodesic and a closed geodesic?
Well, there are an infinitely many closed geodesics on this manifold. And in principle, I think I could also account for them, and I don't suspect it will change the result more than by a multiplicative factor, although I'm not sure. The computation that we did was with geodesics that connect boundary to boundary.
I mean, it's not obvious that the interior of the black hole from the Lorentzian viewpoint will only include such a connected. If the interior is complicated and has handles and so on, then the interior volume could also include.
Well, I think the handles will be located in Euclidean signature and will connect to the bra and the ket. So they'll be like this, and that I wouldn't call necessarily the. this is a question of definition. And in principle, if you want, one can redo the computation, even accounting for these closed geodesics. But the quantity that I defined, I believe, is diff invariant and well-defined.
Sorry, I'm still puzzled about Edward's question. When you say you add, you mean you add lengths of different geodesics?
Yeah.
Isn't that infinity?
Well, no, because you have to take the quotient by this group of large diffeomorphisms. And even though naively you'd think that you're counting an infinite number of geodesics, they're related by the mapping class group.
But geodesics with different lengths aren't equivalent.
No.
to each other.
Geodesics with the same lengths are equivalent. It's about the
okay, sorry.
weighting of the.
But if they're geodesics, if there's geodesics of different lengths, then you take the minimal one?
There are geodesics.
You're
No,
considering
he's taking all of them.
Yeah.
That's the answer to my question.
Yes, I'm taking all of them.
What did Edward say? You add the lengths, but isn't
No, he allows them all. I think he's doing an interval where you specify the length of the green part. And you also specify the length of the red part, and then you calculate the partition function as a function of that data.
That's right, and then I'm integrating over the possible lengths with the appropriate probability that's associated to, that can be computed geometrically.
So maybe a related question, he didn't draw in this illustration, but do you consider geodesics go into the, say, the holes of some higher genus surface and come back? Or you only say, so for example, the first one coming from, you go to the nearest hole, but where you go to some other ones?
Yes, I think those are all summed over. Since the computation is done in Euclidean signature, it's a bit, your question depends a little bit on how you analytically continue these pictures, how you cut and glue a Lorentzian portion in them. But yes, I think you account for those as well. We account for literally everything that could possibly occur on any genus surface that connects these two boundary points. Okay, so the reason why.
What about self-intersecting geodesics?
Yeah, I said that we don't account for those because, well, I just defined the volume of the black hole interior to not self-intersect. Or I would like the black hole, the slice of the black hole interior to not self-intersect. Good. So to show that the computation is similar to that of the spectral form factor, I won't go into detail. I'll just point out that if I glue to the figures that I previously shown, these portions of a hyperbolic disk, I obtain precisely the surfaces that contribute to disorder in the genus expansion in the spectral form factor. So now let me show you what the spectral form factor is and how the spectral form factor is related to the expectation value of this geodesic length. It's convenient to express the spectral form factor in an energy basis for a Laplace transform. So the spectral form factor is just, as you all well know, the product of two partition functions, one at beta plus IT and one at beta minus IT. The nice thing about this expansion, writing it in this way and in an energy basis, is that I simply express it in terms of this spectral correlator. And very many things are known in this spectral correlator in random matrix theory, and I'll review what is known in a second. Similarly, I can express the length of the operator after summing the contribution of all surfaces in terms of precisely the same object, the spectral correlator rho of the matrix integral that Schatzinker and Stanford suggested. The only difference between the two expressions is that here I have to insert an expression of what the length operator is in terms of the energy basis E1, E2. This can be obtained geometrically. There's various ways to do the computations. But essentially the expression for this length operator is the following. Importantly, the expression for this length operator is completely independent of e to the S0. So all the information about the genus expansion just enters through these rho correlators. And for those of you that have done the JD computation in detail, that's simply because the information about the Weil-Petersen volumes is all captured inside of the rho correlator. So as I was mentioning, I want to compute this observable at late time. So I have a Fourier transform that I have to evaluate at late time, and time multiplies the energy difference E1 minus E2. So the integral is actually dominated by the regime in which E1 minus E2 is very small. So I'm interested in a regime in which from the matrix integral perspective, I'm probing eigenvalues that are extremely close to each other. And in this regime, the formula that I wrote previously for this length operator has a double pole in E1 minus E2. It goes like 1 over E1 minus E2 squared times some function of E1 plus E2 as E1 goes to E2. So why do I care about the regime in which the energies become close? Well, luckily, in the regime in which the energy becomes close, the spectral correlator that I just talked about has a universal formula. And this universal formula is the bread and butter in random matrix theory and captures the eigenvalue repulsion in random matrices. So here, instead of working with energies, I'll work with square root of the energies. It proves way more convenient for the formulas afterwards. And on the right-hand side, I'll plot what the spectral correlator looks like as a function of the energy difference, S1 minus S2. And on the right-hand side, I'll plot the corresponding contribution to the spectral form factor. So there are three pieces in this spectral correlator that are universal. The rest vanish as omega goes to 0 or as the energy difference goes to 0. So the first is just a product of rho of S1, rho S2. Here, rho hat is just a normalization of rho where I exclude the factors of e to the S0 to make it more apparent where e to the S0 enters in the computation. So this starts out by being approximately constant in the spectral correlator. And if I plot the contribution in the spectral form factor, this is just a decaying function. And this is actually related to the paradox that Juan brought up for bilocal observables in the eternal black hole. This just corresponds to the classical black hole contributions, but there's a correction. A leading correction comes from the wormhole that has no handles on it. And this wormhole contributes a factor of 1 over omega squared to the spectral correlator. So I plotted it here, the sum of the two I plotted on the right in yellow. And in the spectral form factor, it's what leads to the ramp. And finally, this wormhole contribution receives a further contribution that's no longer perturbative in e to the S0, so does not have a straightforward geometrical meaning, but is universal. It's given by the sine kernel. So this is an oscillating function whose period is proportional to 1 over the average net energy density. So this, it means that the period of this function goes like e to the minus S0. And since this is in a periodic function, it means that, since this is in a periodic function, it means that the sign correction is doubly non-perturbative. And importantly, I wanted to remark that this spectral correlator has the feature that if I really expand that omega and values of omega that are as small as possible, so even smaller than e to the minus S0, the entire thing goes to 0. So this is just the fact that it goes to 0 is just the sign of the eigenvalue repulsion that I mentioned earlier. And if I, instead of doing this in a matrix integral, I just took an individual matrix and plotted how the spectral form factor looks like, it would be self-averaging. So the noise would be would be much smaller than the signal until the ramp time, after which the noise becomes much larger than the signal. And I didn't represent this on the right-hand side. So let's now take the formula for the rho correlator and plug it into the formula for the volume. The first observation comes from looking at the semi-classical disconnected piece. This is just the two individual black holes. The individual describing the geodesic in a single eternal individual black hole in the classical solution. And this grows linearly in T, and this is exactly the result in GR. Although this is a bit more general, it tells you that for whatever value of rho that you choose, even including perturbative quantum corrections in G Newton and rho, you will obtain a linear piece in T, and this is a result that was obtained in the past by Henry. So this is universal and is independent of rho of E. And the second piece that I'll plot are the non-perturbative corrections. I won't go through the wormhole contributions, as that turns out not to be important. So the non-perturbative correction at early times start out at precisely 0. And eventually, because here there's the scale e to the s0 entering in the sign kernel, at time proportional to e to the s0, they start deviating. And at late times, it's very important that this relative coefficient between this term and this term is fixed in such a way that if I take the expansion around omega equals 0, I find that the rho-rho correlator vanishes at omega equals 0. So it turns out that because of the vanishing of the rho-rho correlator at small energy differences, there's a pretty powerful consequence, which is the slope of at late time of the curve coming from the non-perturbative piece is exactly equal but opposite in sign to the slope in the linear growth in time in the disconnected piece. So let's sum the two. If you sum the two, you find that the volume indeed plateaus. It starts out linear in T, and then at a time and a value proportional to e to the s0, it turns around and plateaus as promised. Okay, and I want to emphasize that this is, you might think that the plateau and the spectral form factor and this plateau are the same thing. I want to emphasize that they're very different. In the plateau and the spectral form factor, the disconnected component of the rho-rho correlator played no role. That just simply decayed with time. Here, the black hole itself plays a very important role. The disconnected contribution of the rho-rho correlator grows linearly with time. So the cancellation that happens here in order to see the plateau is completely different mathematically than the cancellation that occurs in random matrix theory in order to see the plateau in the spectral form factor. And there's another consequence of that I think is very interesting, which is we can look at how the noise of this plot would look like if I studied a single member of the ensemble. So I could define the variance of this quantity by studying the expectation value of L squared minus the expectation value of L everything squared. And this is a quantity that I can again compute in geometry. Again, I could use tricks related to the spectral form factor, and I get a complicated expression for sigma of L that depends not on the rho-rho 2-point function, it now depends on the rho-rho 4-point function. And it depends in a way on the rho-rho 4-point function that's very different than for the spectral form factor, for which the noise is proportional to the signal. Here we find that this variance is proportional to square root of p. So we find that the standard deviation in the length expectation value is much smaller. So the standard deviation is much smaller than the length for times that are t smaller than e to the 2s0. So wherever I am in this plot, even past this time t proportional to s0, this quantity is self-averaging as opposed to the spectral form factor. Which brings me to my second point, which relates to Jorrit's talk from a couple of minutes ago. So in Jorrit's talk, instead of studying JT gravity, we studied a deformation of JT gravity that included local interactions. These local interactions slightly changed the geometry from being hyperbolic into having some wiggles that are of order e to the minus s0. And I not only have these local interactions, I also have non-local interactions that connect the asymptotic portion of the space-time to these closed universes that also contain additional wiggles. So now the question is, how can I measure the length of this red curve that starts on the asymptotic boundary in this setup? So again, I could do precisely what Jorrit suggested, and I could expand this potential in branes. And I obtain the following set of geometries. I have to measure the length of the black hole interior on the disk geometry. I have to measure it on the half wormhole geometries. There's two possible ways of going around the half wormhole. And finally, there's an additional geometry which does not cancel in this case, precisely because these correlations that I drew previously could be on either side of the red geodesic. And if I do the brane expansion that Jorrit said previously, I'm left with this shape as well. But I could again use the same geometrical tools that I used to compute the length operator in the genus expansion to compute the length operator in this theory. And I end up with the following formula. So what I want to emphasize is that here, the Z-brane, the particular choice of Z-brane of B that Jorrit describes, uniquely determines a boundary Hamiltonian. And with this boundary Hamiltonian, if it has eigenenergies EI and EJ, then the length operator could be expressed in the following way. Here I have precisely the same expression that I showed you previously in the for the length operator in the continuum within the continuum integral. So anyway, the thing in the denominator is that. But now I actually just end up with the sum over eigenenergies. So it's like a discretized version of the formula that I showed you before, but now essentially the rho correlator is just given by a sum of delta functions, which is what we expect in the discrete theory. And this also answers the question of what this length operator L of t is in the random matrix theory, namely for each choice of matrix, given its eigenvalues EI, this is the expression of the length operator. Now, since I can reintroduce an average over H0, this means that the length of the average of this length operator when I average over S0 is reproducing the resultant JB gravity. And since sigma L is much smaller than L for very long times, it means that the expectation value of L in the factorizing theory is the same as the expectation value of L in the theory with wormholes. So essentially what's happening is that wormholes reemerge for self-averaging quantities, and I just wanted to take the volume as a quantity that emphasizes this. So since the behavior of the volume solely relied on having the appropriate pole structure as E1 goes to E2, we can think of a simpler quantity that behaves precisely in the expected way as the volume of the black hole interior, and is self-averaging for any holographic theory. So namely, it's this quantity, which looks like the spectral form factor, it just has a double pole in the denominator. And we will call this quantity the spectral complexity of the thermal field double state. So what is this? This is a meeting about quantum information. I should ask, what is the information theoretic meaning of the spectral complexity? And in order to explain that, it's useful to introduce the following, to define the following quantity. I'll define the thermal average double density matrix as an average over density matrix of pure states of thermal field doubles at different times, weighed in the same way at all times. So as the time goes to 0, this thermal average double density matrix is just the density matrix of a pure state. And as time evolves at t going to infinity, it becomes a state called the thermal mixed double density matrix, which was discussed by Herman in a paper a year ago. And it's a very mixed state. So it goes from being a pure state to a very mixed state. So what can we characterize about this density matrix? Well, one thing that we're interested in is in a regularized version of the rank. And one such measure is this factor, this dimension called the effective dimension introduced by these authors, which is 1 over the trace of this density matrix squared. And we can view this quantity as a measurement for the expected span of all the states that contribute to the thermal average double. So for example, a mixture of n orthogonal states of equal probability has the effective dimension equal to the number n of orthogonal states that contributes to that state. And I can explicitly compute what this quantity is if I start out from the thermal field double, and I obtain a quantity that's explicitly connected to the formula that I wrote for the spectral complexity a few slides back. Okay, so now let's plot this quantity again. So here I'm plotting the effective dimension as a function of time. At early time, this dominates because this contribution is suppressed in the genus. Z of 2 beta over Z of beta squared goes like e to the minus S0, while the ratio between the spectral complexity and t squared goes like order 1 early times. I mean at times t smaller than e to the S0. Now, at later times, these two quantities switch dominance. So eventually, what starts dominating is the effective dimension of the thermal mixed double state that Herman talked about. And what this means is that the effective dimension plateaus, and this is a signature of the fact that the thermal field double states have started spanning the entire Hilbert space. So essentially, the fact that this spectral complexity grows linearly with time implies that the thermal field, roughly the Hilbert space spanned by the thermal field double space also grows linearly with time. And eventually, since the Hilbert space runs out, there's no more new orthogonal states, this effective dimension plateaus. So this D effective appears to be a remarkable proxy for complexity. So to summarize, I've shown you that with a non-perturbative definition of the volume grows linearly with time up to times exponentially that are exponentially long in the entropy, and at an exponential value, it plateaus. The noise is very small, which means that if you plot this quantity in most chaotic theories, it will look precisely the same and will have very little noise. And it's insensitive to whether the theory factorizes or not, or we're considering an ensemble. And this spectral complexity determines this more information theoretic quantity that I called the effective dimension that captures the growth of the span of thermal field double states or potentially more generic initial states. Now, one question that I would like to ask this audience is whether there's any chance to connect, since the time behavior of both the effective dimension and circuit complexity looks so similar, I'd like to ask whether there's any chance to connect the effective dimension to the circuit complexity, at least in some circuit models. Perhaps this effective dimension places the lower bound. Thank you very much. Yes.
So everywhere where you were talking about times of order e to the s naught, did you really mean e to the 2s naught?
No, I think
You really meant e to the s naught?
Yeah, I meant e to the s naught. The only place where e to the 2s naught appeared was when the noise was for the noise. It was essentially when the noise became of order, the same order as the signal.
Because I guess maximal complexity should be e to the 2s naught.
Well, I think if I start with a thermal field double state and evolve with a regular Hamiltonian, I think it should be the s naught.
So I just think because the number of unitary, somehow the number of for unitary to become generic takes
you have energy conservation.
Yeah, you have energy.
Oh, I see. So because of
that's why I said if I evolve the thermal field double state.
Is it S naught or S of beta?
So it's okay, e to the s naught, and then the exact time at which the plateau occurs does depend on beta, but we couldn't quite get it to be exactly e to the s of beta. There were small corrections to that depended on beta. Yes.
Are you also claiming that this scenario also changing the geometry behind the Poincare patch? Because I assume that Poincare patch corresponds to zero temperature, and so zero temperature entropy also exists in Poincare patch.
So I think at zero temperature, things are a little bit more complicated because as far as I remember, this length operator, the value of the plateau of this length operator diverged as beta went to infinity. But I have to remind myself. What I showed you was the e to the s naught factor. I didn't show you the beta dependence of the plateau.
How is this related to the story of Phil Saad, who had the length relaxing due to sort of its process?
Yes, so in Phil's story, he studied the 2-point function, the probe 2-point function, and essentially it's a very, the story is very similar in the sense that to compute the probe 2-point function, you could use precisely the same technique as I showed in the beginning, and that's what Phil used as well. The difference is that if one computes the probe 2-point function, then the geometry that becomes important. So initially the 2-point function decays as a function of Lorentzian time. And the geometry that becomes important is the genus 1 geometry. So that leads to a growth of the 2-point function in Lorentzian time. And it's analogous to the ramp that you see in the spectral form factor. In our case, the problem, or rather the unexpected feature, was that the black hole contribution by itself was growing with time. It wasn't decaying with time, as in the 2-point function. So the very nice thing is that in our case, these non-perturbative effects cancel this growth. So I think it's slightly different. I think the story there is much more similar to the spectral form factor. To that in the spectral form factor. I don't know if that fully addressed your question.
Yeah, in terms of your last question about does this new quality kind of connect to standard circuit complexity?
Yeah.
Have you considered how like ensembles, like what the effective dimension can be of say ensembles of Clifford states or something like this, which has a lot of dimensionality but never gets super complex?
Right. So that's something that we're considering. We're considering how to consider this, how to compute this effective dimension if instead of evolving by time-independent Hamiltonian, you evolve it through a random circuit, and trying to see the dependence of this effective dimension as a function of that length of the random circuit. So the reason I think they're related is because it's a measure of how much of the Hilbert space you've explored, which is in some sense what complexity is as well.
Let's thank Luca for a wonderful talk.